It's a great honor to be here. Thank you for the invitation. And today I am going to give you a summary of some of the work that's been going on in the Pyrenees over the last 10-12 years. There's been a huge effort in France through these various projects that are shown on the base there, Orogen, Pyramid, and RGF Pyrenees, to have a new look at the French side of the Pyrenees, because of course, as we know, the Spanish side is extremely well known because of the huge amount of work there and the quality of the outcrops, but the French side has been rather in the shadow for a long time. So I can't cover everything. I'm not going to talk about salt tectonics today. I had to make some decisions, and I want to talk about the ideas of that have come out about what this orogen is and its history. So the next slide, please. As we saw yesterday, can I have the next slide?
Not by me. Are you controlling these, Rosanna?
Rosanna, yes. Okay, thank you. As we saw yesterday with Hakan's talk, orogens are considered as the final product of a Wilson cycle, and this figure, which is fairly standard, shows a full Wilson cycle, which involves the rifting of a stable plate, the creation of passive margins, the production of oceanic crust, a full oceanic basin, then passing into the convergence system with the creation of a subduction zone, and finally going into collisional orogeny. However, every orogen has its own peculiarities, and if you go to the next slide, please, the Wilson cycle that we see in the Pyrenees is actually a highly curtailed cycle. You could describe it as a low extension, low convergence Wilson cycle. And that's what I've tried to show in this cartoon here. So let's start at the bottom. The rifting that we see never produced oceanic crust. It produced exhumed mantle, so we have a low total extension. Then the rifting ended at about 92 million years in the Cenomanian, and we started having post-drift cooling. However, the post-drift cooling only went on for about 8 million years before convergence started. Now, we had no oceanic crust, so we have no subduction preceding collision of the continental plates. So we closed our rift, and yet at the end, we see that the Iberian plate, shown in orange, is subducted below the European plate. So some of the questions that we can ask are, well, how do we go from rifting to an asymmetrical orogen without subduction, asymmetrical subduction preceding? What happens to in the beginning of this convergence to establish the asymmetrical system? So I'm going to show you some of the details. Next slide, please. So to start on the largest scale, the Pyrenees is one of these small orogens in the Western Mediterranean that developed due to the collision of the African plate with the European plate. The Pyrenees is due to the convergence of the Iberian microplate, if you like, with Europe. It goes from the Galicia margin in the west right through to Provence in southern France, where it's overprinted by the Alpine orogeny. I'll be mainly talking about the Pyrenees sensu stricto, which is between Spain and France. Next slide, please. The Pyrenees is a world-class case study for collisional orogens. It's cited as one of the generic examples. As I said, the Pyrenees, the southern Pyrenees, is a spectacular fold and thrust belt, very well known for its outcrops, as shown in the top two photographs. However, the French side, due to the high rainfall, has not got such a good reputation as shown on the lower left-hand side. However, we do have some excellent outcrops, I assure you, for pacing all the work that I'll show you in the sequences afterwards. Can I have the next slide, please? To summarize the geological architecture of the Pyrenees, it's a small double-wedged collisional orogen with a low total convergence between 90 in the west and 135 in the east. The pro-wedge on the southern side consists of the axial zone, the South Pyrenean zone, the Ebro Basin, which is the Foreland Basin, it's important to emphasize that there is no synorogenic metamorphic internal zone in the Pyrenees. The axial zone is actually a series of thrust sheets or blocks of Variscan basement with its Paleozoic cover, which is not affected by any synorogenic metamorphism to do with the Pyrenees. The Retrowedge on the north side consists of the North Pyrenean zone, which is this very narrow dark green and light green to the north of the axial zone. This is our northern or Retrowedge fold and thrust belt, and the very large Aquitaine Basin to the north. Importantly, the inverted Aptian-Cenomanian rift is preserved in the North Pyrenean zone to the north of the axial zone. This rift system has very spectacular characteristics. It's shown in that big red dot on the cross section below. It's characterized that the remnants that are preserved include exhumed mantle peridotites, often serpentinized, and high temperature syn rift metamorphism. And I'll show you some examples of that. As you see on this interpreted echors or deep seismic line through the center on that line in the map, we see that the Iberian plate is subducted below the European plate. Next slide, please. So these are some examples of the rocks that we find in what we call the metamorphic internal zone. This part of the rift system, which records mantle exhumation and syn rift metamorphism. So on the bottom from left to right, we have got fractured marbles that record this high temperature metamorphism. We have metasomatism and albertization of basement rocks shown in the second photo. In the third, these are breccias of serpentinized peridotites and in a sort of breccia with carbonates. And then the final photograph is of the Lertz peridotite body, which is one of the largest blocks. It's about 3 kilometers long of peridotite. Now, the presence of these indicators suggest that the application of a hyperextension model is appropriate to this rift system. This is shown by, this is a publication by Julie Tugand. It's Generato Manichal's group that have developed this idea that the exhumed mantle is very characteristic of slow amagmatic stretching. And can you press the next three times, please, because it's animated. So we're going to look at all the details I show you on the bottom is from that red circle. The next one, please. The next two. 1, 2, yes. And the next one. Yeah, these all these details have been very intensely studied by Yves Le Gabriel and his colleagues and other colleagues to try and understand serpentinization, flow of very hot fluids, metasomatism, and these are the kind of spectacular models that they're developing of the interaction of all these different processes on these hyperextended margins. This is not my expertise, but it's very important to mention all this work, which has been really advancing very quickly in the Pyrenees. Next slide, please. Now, during this Apto-Albian rifting or Apto-Cenomanian rifting, the plate reconstructions have been highly discussed, and this figure shows you 3 of the types of models that have been developed. These are from they are constrained by the magnetic anomalies in the northern central Atlantic. So the top one suggests sinistral transtension with the eastward movement of Iberia with respect to Europe. And this would develop a transtensional rift system between Iberia and Europe. And this is the model that I think it best fits, but not everyone agrees. The second one is a rather extreme model, which gives an anti-clockwise rotation of Iberia, which opens an ocean between Europe and Iberia. But of course, we have no evidence for oceanic crust but it has to be included. It's one of the models. And the last one suggests that any strike slip between Iberia and Europe happened before Aptian-Cenomanian rifting, probably in the Jurassic, and that this allows the rifting to be pure shear rifting and then closing, so a sort of accordion tectonics is allowed by this model. Next slide, please. So that's the inheritance. Now, when we get to convergence, the plate kinematics are much more clearly constrained, and I'm showing you here a reconstruction of the plate kinematics by Machiavelli et al. And in this graph, she shows the north-south component of the convergence. There's a very small strike slip which she's removed on 3 cross sections through the Iberian Europe margin, and you can see that in the east we have higher convergence than in the west. And you can also see that there's very clearly 3 phases in this history of convergence. So we start in the late Cretaceous with very slow convergence at less than 1 millimeter a year. In the Paleocene, we have everything seems to stop, and this is also true for the African Europe overall convergence. And then in the Apresian, in the Eocene, and the Oligocene, we have our main convergence and collision, which ends in the Aquitainian, with a convergence rate estimated at 2.5 millimeters a year. Next slide, please. So what we're going to do now is focus in on the Northern Pyrenees and have a look at the structural style and the basins. As Rob said, I work a lot with structure and stratigraphy and sedimentology to try and reconstruct the history of deformation and the interaction with sedimentation. So I'm going to focus in on the centre-eastern part of the Northern Pyrenees. Next slide, please. And to show you some of these, some cross sections. So these are 4 cross sections which are shown in the map. The most easterly one is S2, and the most westerly one is S5. Now, in grey is the basement, in pink is the Kuiper evaporites, blue Jurassic, dark green are the Sin rift, this Aptian-Cenomanian rift event. Okay, those are the inverted rifts. And then the Foreland Basin sequence is shown in 2 colors. The light green is the Upper Cretaceous Foreland Basin, and the orange is the Cenozoic, so Eocene, Oligocene, and some Miocene. What you see is that there is a very definite, thick-skinned style of deformation. The basement is involved in the deformation here. The fold belt is extremely narrow. The shortening is very low. You can see the estimates on each cross section from 30 kilometers through to 24-18. So this is the northern retro-wedge accommodates about 20%, 15-20% of the total shortening in the origin. And this is typical of the relationship between pro-wedge and retro-wedge. The deformation style, as I said, is thick-skinned, but there is a very strong decoupling on the Kuiper evaporites, and you can see that above the Kuiper evaporites, particularly on the top cross-section, is showing a folding, and some of this folding is actually related to diaperism. So we have to be careful when estimating the shortening in these salt-rich systems. Now, the other thing I'd like you to see is that the basin is actually dying out eastwards. So the whole Foreland Basin is dying out eastwards, and it's not. One thing I forgot to say earlier is that the Gulf of Lion is a backarc extension which actually destroyed the most easterly part of the origin in the Oligocene. So sometimes we know that we've lost a lot of the eastern part of the orogenesis due to that. Next slide, please. Now, if we take the S3 cross-section, this is the work of Arjen Grol, which is published in Tectonics. And he worked in great detail on the cross-section S3, which is shown on the top there, where we have about 18 kilometers of shortening. And he reconstructed this and compared it to the equivalent cross-section on the other side of the origin, which is that of Jama Vergès, which is on the bottom here, the lower section. The lower section shows you very nicely the thin skin tectonics that we see in the southern part. Now, if we go to the next slide, please. what he did was he reconstructed in time and space the activity on the faults and how the deformation is distributed through time, from the early Cretaceous through to the Oligocene. Now, what you see on these graphs is on the left-hand side is the Southern Pyrenees, and on the right-hand side is the Northern Pyrenees. Time is the vertical scale, and the horizontal scale is as on the cross sections. Now, if we take the upper two graphs, you can see that in phase one, in the early Cretaceous, we are inverting the normal faults of the rift system, which are preserved in the Northern Pyrenees. There are some of these inverted faults in the Southern Pyrenees, for example, in Petroforca, but there's very little preserved there. At the same time, at this stage, we are also closing the mantle domain. Right, so we have to close the exhumed mantle domain, and we have some shortening and inversion of the rift faults. Then we have the quiet phase shown in red, nothing much is happening. And then in phase three, the main collision, the whole system becomes asymmetrical. In other words, the deformation is focusing in on the pro-wedge, and we have on the left-hand side, you see the fault activity migrating southwards with time. Now, on the lower graph, you can see the Pinchout migration. That is the Foreland Basin boundary, outer boundary, is migrating southwards onto the foreland. And when we go into the main collision phase in the Eocene, it accelerates to about 7 millimeters a year. It's 2 millimeters a year in the earlier phase. The deformation front is migrating very rapidly to the south also. While to the north, what you would expect is that once the deformation focuses into the pro-wedge, there will be no more deformation in the retro-wedge. But there is, in fact, we still have thrusting, we still have the deformation front migrating and the Foreland Basin migrating. Now, so the first big point I want to make here is that the pro-wedge and retro-wedge work together. They are very strongly connected. They evolve together. And then secondly, on the right-hand side, we have a comparison between Machiavelli's plate convergence rates in green and with the shortening rates that Jan reconstructed on this cross-section. And you can see that the phases connect. They correlate. So there's a very direct relationship between plate convergence and shortening phases within this origin. Okay, which is a very gentle shortening overall. Next slide, please. So now we're going to look at the Foreland Basins. As I said, we have two big Foreland Basins, and the Aquitaine Basin to the north, the Ebro Basin to the south, and on the right-hand side you have the isopacts. To the north you see a very broad Aquitaine Basin that becomes thicker to the south, so very nice asymmetry, typical of Foreland Basins. The little black dotted lines are salt diapirs. To the south, the Ebro Basin has got a complex geometry, not so clearly asymmetrical, but that's because we have a lot of thrushy top basins in the South Pyrenean units. So we have between 4 and 5 kilometers on both basins. So they really are both of equal size and equal importance. Next slide, please. If we look at the subsidence on these two basins, so the Southern Pyrenees is on the left and the Northern Pyrenees is on the right. The upper graphs are total subsidence based on boreholes, and the tectonic subsidence is calculated and presented in the graphs below. Now, what you see in the Retro-Foreland Basin is that we have a full history of subsidence for the whole of the orogenic history from 84 million years right through to the Miocene. We see that there is over 4 kilometers of sediment deposited over this period of time, okay, about 60 million years. And we see very clearly those three phases, the early convergence, the quiet phase shown in blue, and the main convergence in the Eocene and Oligocene. In contrast, in the Southern Pyrenees, we have hardly any history of any evidence preserved of the early phase. But the main phase is, of course, the main collisional phase from about 55 million years onwards. And during this phase, half the time we deposit the same amount of sediment, so over 4 kilometers. But it's related to the main convergent phase. So I think one of the main things I want to say about this is about the Pyrenees and the advances we've made is that Up to now, because most of the research has been done in the Southern Pyrenees, most of the focus and understanding of this orogen has been the main collision phase, and the integration of this early phase during the late Cretaceous and this quiet phase in the Paleocene is quite new and important. Next slide, please. So the thinking about Foreland Basin evolution and including in the Pyrenees, has developed these, generated these models, and this is one that I want to compare to the data I've shown you. This is the idea of growth and steady state within an orogen. This means that a Foreland Basin has a record, this two-phase record, where in the growth phase, this means when the topography of the orogen is growing, you have got outward migration on both sides of the orogen. Okay, the retro-wedge is on the right, the pro-wedge is on the left, the vertical scale is time. So you see outward migration of the two basins, okay, during the growth phase. And then in the steady state phase, which means that the orogenic relief has stabilized, that means the erosion and creation of relief are equal. We have got a huge amount of sediment focusing into the pro-wedge, so we have a very rapid on-lap and outward migration of the orogen. All the sediment is focused in there, while theoretically on the retro-wedge side, the basin should become static and we should have very little sediment going in there with this condensed interval representing the steady state phase. However, when we look at both sides of the Pyrenees, what do we see? We see that the pro-wedge side, the Ebro Basin, fits perfectly the model. It does exactly what is predicted. However, the Aquitaine Basin is not behaving as predicted. This, on the right-hand side on the graph, what you see is the on-lap history on, I think there's 5 cross-sections in there. And what you see is that overall, it's migrating at a steady state through the early phase, through the main collision phase, and maybe with a bit of quiescence or stasis during the quiet phase, phase 2. So something else is driving this basin. This is not just the orogen that's driving this basin. So this is the question we asked. Next slide, please, about what's driving the subsidence and the dynamics of this basin. And this was the thesis of Paul Engrand, which is published in Tectonics. And Paul basically went back and looked at the crustal structure below the Aquitaine Basin, and he mapped out the main Aptian rifts that underlie the western part of this Foreland Basin, and he was able to calculate with various data sets the beta factor or the stretching factor for these rifts, and that's shown on the map on the left-hand side, where you can see that in the Arzac-Romange area we have got betas up to 1.6. He then, using a very basic uniform stretching model, calculated the predicted thermal subsidence, post-rift thermal subsidence that you would have above these rifts. And then he estimated how much of this thermal subsidence would be ongoing during convergence. Now, if you remember, I said that the rifting ends at 92 million years. The convergence started at 84 million years. That means there's only 8 million years between the two. Now, normally, a rift requires about 50 million years. Standard rift, standard continental crust, requires 50 million years to thermally re-equilibrate. This is called the thermal time constant. So assuming a thermal time constant of 50 million years, Paul was able to calculate and predict how much thermal subsidence there would be ongoing, continuing during orogenesis in this basin. So essentially what we're seeing here is superposition of thermal subsidence and orogenesis. Then he took 2 cross sections. He did some more, but I'm showing you 2 here. The westernmost profile shown in white on the map, he analyzed in collaboration with Tony Watts to look at what was controlling the subsidence. How can we explain the subsidence? And basically the 2 blue lines that you see, I'm sorry, it's a bit small. The dark blue line is the observed base of synorogenic sediments, and the light blue is the predicted thermal subsidence, and they correspond perfectly. So we can explain the substance, synorogenic substance in the Western Aquitaine Basin as 100% post-drift thermal substance. When we get into the center, which is the second profile, we need the thermal substance. The rifting is less. We have the topographic load, and we also have overthrust blocks of peridotite, which are hidden loads within the orogen. Next slide, please. So that's the Aquitaine Basin is not a simple Aquitaine Foreland Basin. So the last part of the talk, I want to talk about early convergence and this transition to main collision. In other words, how do we go from a rift to an asymmetrical subduction of continental crust? And I come back to Arjan's work, where in his restored section, he represents here on the bottom cross section a hypothetical condition just before convergence. Now, we don't know the width of the exhumed mantle domain. Generally, people say 50 kilometers, but we don't know. We don't know if it was continuous or just in blocks. So here we have got the exhumed mantle domain. We have a narrow rift to the north and very narrow margin to the south. There's probably strike slip going through here, which he hasn't represented. Then in the upper one, what he's done is he has closed the mantle domain. This is in the early phase, okay, early convergence. He's closed the mantle domain mainly by subduction, and he's inverted the rift to the north. And in red, these are the metamorphic sediments with the breccias, the various breccias, which have been abducted, if you like, onto both margins. Of course, N is the Nogueres basement thrust sheet, and that's been uplifted, and everything that you see above it has been eroded. So, of course, this is there's a certain amount of speculation in these models. What I'd like you to notice also is the basin, the Cretaceous basin. So the light green basin is basically the beginning of the thermal subsidence phase, and then it continues as a basin during this earliest phase of orogenesis. Next slide, please. So we have no relief during this early. Next slide. Thank you. We have no relief in this early orogenic phase in the late Cretaceous, and this is shown in this paleogeographic reconstruction. There's a lot on this, but what I want you to see is the Pyrenean Trough. This is this continuous flexural post-rift basin that covered the whole of the orogen. The shortening and closing of the mantle domain was going on underneath, and the sediment was supplied from the Massif Central and from the east, from a poorly constrained massif to the east, and we have all these huge amounts of turbidites going out to the west. It opened out into the Bay of Biscay. Now, this raises some important questions, and that is, how do we interpret orogenic cooling that is detected by low temperature thermochronology when we have no relief? So this is the next slide. It's the work of Sebastien-Ternois, who worked on the Agly Massif. Can I have the next slide? Yeah, who worked on the Agly Massif in the Eastern Pyrenees, which is a small basement massif in the North Pyrenean zone. Click it twice, please, Rosanna. Yeah, perfect. He did in situ zircon, uranium, thorium, helium dating of the basement rocks of the Agly Massif. The results are shown on the right. It's published in Tectonics. And what he modeled these results, and he showed in the light blue line on the upper that there is a cooling phase in the late Cretaceous. Now, we can't explain this by the standard uplift and erosion, so he explained it in the cross sections on the left by sandwiching, during early convergence, sandwiching the hot Agly Massif between the cool European plate and the cool Iberian plate, and that's shown on the second from the base cross section. Okay, so this is a new way of explaining cooling in an orogen that's worth thinking about when you have little or no relief being developed. Next slide, please. Now, another aspect of the early convergence is that there are many signals of the same age in the far European plate. And so we have a far-field signal for early Pyrenean convergence that needs to be thought about. And this is the work of Armin Dielforder, where he showed that these Central European basins up in Northern Europe, the CEBS, these are Mesozoic basins that underwent inversion at exactly the same time, i.e. the late Cretaceous, as the convergence started, shortening started in the Pyrenees. And this is shown in the chronology on the right-hand side. So on the very right-hand side, you have the basin inversion of these Central European basins, and in the other two, you have got the early subsidence of the Foreland Basin in the Pyrenees and the shortening. But what you see also, which is remarkable, is that the inversion of these Central European basins stopped abruptly in the Daunian at exactly the same time as we had this pause in the Pyrenees, this stasis phase, which is shown in grey on the timescale. And the basins in Northern Europe underwent stress relaxation and they never reactivated again. However, reactivation and ongoing convergence focused into Europe. So during the early convergence, we have a far-field transmission of stress. During the main collision, we no longer have that. Now, how can we explain that? So the next slide shows the reasoning that we came up with. So basically, in the top cross section in this cartoon, we have got our rift. This is a strong boundary between the Iberian and the European plate, and which allows enough stress, which Armin calculated 3 to 4 by 10 to the 12 Newton meters. This was enough stress to translate northwards and invert the basins in Northern Europe. However, we have to create an asymmetrical new plate boundary to allow the subduction of the exhumed mantle domain and the Iberian plate. So this is our new plate boundary that we create, which instigates the asymmetry that we see in the main collisional phase. And once we establish this plate boundary, we break the mechanical coupling between the two plates, and all the deformation focuses into the origin. Those basins in the north are no longer inverting. And next slide. Armin was able to model this in collaboration with Sascha Brunn to show this, this symmetrical distribution of deformation that is replaced by asymmetry once we establish this new plate boundary fold. This is in his paper, so you can have time to look at it in peace and quiet if it interests you. So I'll finish there. The last slide is basically to say that the Pyrenees is a very beautiful example of a low extension, low convergence origin at the end of a very short, it's not a short Wilson cycle, it's actually quite long, but the amount of deformation in both the extension and convergence phases is quite low. The other essential point is that it inverted a hot rift. So we see that the inversion of a rift involves this initial symmetrical inversion, then the creation of a new plate boundary, and the establishment of the asymmetrical convergence focused into the pro-wedge. The hot rift had a major influence on the Retrowedge-Foreland Basin, and finally, what I showed you in the beginning is that plate kinematics can be directly related to the deformation and the subsidence phases that we have documented in the Pyrenees. Thank you for your attention. I hope I wasn't too long.